All right, everybody, 2 o'clock. Welcome back to your favorite class. Rawr! Okay, a couple of announcements. First, exam 1, graded. Awesome job. You guys crushed it. All right, that went more smoothly than I could possibly have imagined. So everybody got their work in. Everybody had a good job setting up their camera. It was nice to actually see all of you. So that was cool. And generally, you guys did very well. I think average was like high 80s. So you guys brought it to Pound Town. Good job. All right. So keep that up. Normally I would go over the exam right about now, but we don't have time this week. And that's because, surprise, Friday is a university holiday, which I didn't even really know about until like 5 days ago. Okay. So this Friday, we don't have class. Though I will still be here at the normally scheduled time working example problems if you want to come see it. If you can't come at that time, I'll post it to YouTube just like I post every lecture. All right. If you need that link to the YouTube page, go to Blackboard. It's there. All right. So good job on exam 1. That's all I'll say about it. Solutions posted. Go check it out. Generally, you guys did very well. Number 1, 3 a little bit, but other than that, very good. Okay. Keep that stuff up. Good job. All right. Next. Homework number 3 has been posted. It's on Rigidbody Kinetics, which is the topic that we'll cover this week. So we'll get through the material through Thursday. So you should be able to complete the homework starting on Thursday. And the homework will be due next Tuesday when we start lecture. Okay, so 1 week from today, right at this time, homework number 3 is due. All right. So again, I'll just say that the 14th is this upcoming Friday is a holiday. So April 10th is a holiday, which is a little strange to me that we have Easter, sort of a religion-based holiday. Whatever. MSOE is supposed to be non-religious affiliated, but okay, whatever. We have a no class technically on Friday. So I will still be here. I will still do example problems at the time. Come if you can. If not, no big deal. All right. As long as there's one person here, I'll go. If there's nobody here, I won't talk to myself. Okay. All right, so let's start in on new material. New material that we've got going on this week is rigid body kinetics. Okay, so up until now, we've talked about rigid body kinematics. And so I'll just remind you the difference between kinematics and kinetics. Kinematics is the study of the relationship between acceleration, velocity, position, and time. Okay, so over the last couple of weeks, we have talked about relationships between acceleration, velocity, position, and time without any mention of how those things came to be. So typically, if you want to create an acceleration or create a velocity, you're going to have to apply some force or apply some moment to create those velocities and accelerations. Okay, so kinematics is the study of the acceleration, velocity, position, and time. But kinetics is how those velocities, accelerations, and positions are fabricated from the applied forces and moments and so on. Okay, so the most fundamental equation that you know relating these things is something like F equals ma. Force is equal to mass times acceleration. If you want an acceleration, you give it a force. Okay, pretty straightforward. Now, with rigid bodies, that sort of thing still holds. If we want to push a rigid body, we apply a force to it. But now, if we want to spin a rigid body, we have to apply a torque or a moment to it. So we have an analogous relationship like we have F equals ma in your traditional particle dynamics class. We have an analogy for rigid bodies now between what would be applied moments and resulting angular acceleration, which I'm going to derive for you over the next 3 days. All right, so that's what we got going on.
Man.
What?
My man.
Okay, thanks. Please mute your mic, Austin.
You look hot.
Okay, thanks. Okay, someone's been drinking today, it seems like. All right, so let's get on with the lecture. I'm going to flip you guys over to the white pad and we'll go from there. So I have posted a new set of notes, which is the rigid body kinetics notes. So you should all have that available as a PDF on Blackboard if you want to follow along. Okay, so let me get rid of my cats here. Hopefully you guys like my memes. I've started incorporating memes now just because, you know, let's have a little fun in our lives. Okay, so here we go. Let's review what you should have learned in ME2002 about particle kinetics. All right, so that's where we're going to start. review for particle kinetics. All right, so I kind of made mention of this, but let's make it explicitly clear. So a point in space with mass m, if acted upon by a force, terrible, will have a proportional acceleration. Okay, so we can sort of draw this pictorially, where let's say I have some particle here of mass m, and I give it some force here. Let's call this F. All right, it's going to have a similarly resulting acceleration. All right, so I can't draw it on top, but imagine that this arrow is also on top. And if I give this a force, the force that applies will result in this mass having an acceleration of a. All right, so it's this basic fundamental Newton's second law back to the 1500s particle kinetics idea. And so we write this mathematically as our force F is the mass times the acceleration of the particle. This is our relationship between the force that we might apply and the acceleration that you might generate for this particular particle. All right, so we know that the acceleration is the first derivative of velocity. So we can write a little bit modified version of this F equals ma equation, which is relating, sort of writing it in terms of velocity, which allows us to look at the linear momentum of the particle. So this would give us that the force no longer is ma, but is m times dv dt, or since mass is not a function of time, we could write this all together. Sorry, it's a bad arrow. As the force by bringing the mass into this derivative, dmv. dmv sounds terrible. dt. All right, so the derivative of this mv quantity with respect to time is sort of an alternate representation of the relationship between forces and accelerations, or forces and velocity in time. All right, so this is now a little bit alternate, and I want to define now for ourselves a new vector, which is the linear momentum of a particle. So linear momentum of a particle usually is given the letter capital L. Wow, that's a big L. All right, usually given capital L. And this is going to be the velocity of the particle multiplied by the mass. So you've probably seen this before in your particle dynamics class, but maybe not explicitly as the vector L. So if you ever did your impact mechanics in 2002, hopefully you remember your impact. You did a lot of MV stuff. All right, that's linear momentum. All right, this allows us to write sort of an alternate form of Newton's second law. Which is relating the linear momentum to the force. So F equals the time derivative of the linear momentum, which is dl dt, or you might see it written just as L dot. All right, remember, a dot over a variable represents the time derivative. So here, let's be clear that this is the vector L time derivative. Okay, so these are vector derivatives. L vector dot, a little bit strange, but here's kind of an alternate form of F equals ma. Strange. All right. Now, this is all linear stuff. Linear momentum, linear forces acting upon our particle. Now, we have made in the past analogies between linear stuff that we know and angular stuff that we want to know. So in this class, we've had analogies between linear and angular motion by, let's say, we know acceleration in a linear form is dv dt. This is our linear. We can have an angular analogy, which is like the angular acceleration alpha is the derivative of the angular velocity omega. Okay, we've made a lot of these analogies in this class between what would be a linear thing and what is that angular thing. Okay, so my question is, this is a linear relationship here. So is there an angular analogy to this general formulation? So is there angular analogy to what is F equals dl dt? The answer obviously is yes, otherwise I wouldn't be talking right now. Well, I might be talking, but talking about something else. Is there an angular analogy to this F equals dl dt? The answer is yes. But I got to introduce some things first before we get down that pathway. So the answer is yes, but I have to introduce some other things first. Maybe some of you have seen these concepts in your 2002 class. Maybe some of you have not. I'm going to kind of assume that you have not and proceed with that idea. I'm going to talk about particle angular momentum for a short amount of time. Then we'll see how angular momentum of a single particle can be integrated over a rigid body that has infinitely many particles to give you what would be angular momentum of a rigid body. So that's kind of the general strategy that we're going to go through here. Okay, so the answer is yes, there is some analogy to this F equals ma, but let's talk about what that is by introducing some topics that we need to cover to get us there. All right, so the first thing that we need to talk about is the angular momentum of a particle. So maybe some of you have seen this, maybe some of you have not. All right, so this is angular momentum of a particle. All right, so let's draw ourselves a picture here and we'll talk our way through this picture. Okay, sorry, angular momentum of a particle. All right, so here we have a picture. I'll try to draw it sort of as big as I can. And it's three-dimensional, okay? So we have our typical XYZ coordinate system. Here's X, Y, Z. And let's say that there's a point in space. And let's call that point P. And it has a mass of M. And it's located away from the center of this coordinate system with our typical position vector R. You can say R locating P from O if you want, or we'll just say that this is R. If you call this O and you call our point out here point P. All right, so we locate P from O using our position vector, arriving at P from O, which I'll just call little r. All right, so this is kind of our setup. All right, now let's say that it has some velocity in space defined by a vector v. Vp or v, I'm just going to draw as right now. Okay, it's got some velocity. So that means that it will have some linear momentum. Which is in the same direction of the velocity, but scaled by the mass. So that is LP equals the mass times the velocity of P. Right? So this is our linear momentum of this particular particle. And so let's draw that vector here. Maybe let's say this particle P has got some velocity in this direction that results in our linear momentum L, which is our mass times the velocity of our particle Vp. All right, so we have linear momentum, we have velocity, we have mass, we have location, we have all of these things. All right, now we'll introduce the new concept, which is angular momentum. And we'll say that the angular momentum, I gotta move this down a little bit, sorry if people are still trying to copy that image. We'll say the angular momentum is whatever sort of rotation this particle tends to impart around our central axis O. Okay, so the angular momentum, we'll say of mass at P about 0.0 is the following. It'll be given by variable H O. All right, so this is the angular momentum of this particle about 0.0. And the general equation here is going to be the position vector crossed with the linear momentum. And it will be the angular momentum of particle P about 0.0 is the position vector crossed with the linear momentum of point P. Right? So this is your angular momentum of this particle about 0.0. All right. So I'll give you a second with that. And then I will draw what that vector actually looks like on our figure. So this is just like how you would get a moment from a force. R cross F gives M. Here R cross L gives H. It's my angular equivalent. Right? So if I think about my position vector R crossed with my linear momentum in this particular case, I might have a resulting angular momentum that looks, I don't know, something about like this. All right, this is my angular momentum of point P about O. So this is taking basically the cross of R and L. My thumb by right-hand rule would kind of be sticking in what looks like the direction of this HO. Okay, so we can think about if P is on some path defined by this velocity, it's currently like spinning around that particular point with that sort of like angular momentum. All right, that's kind of like the general idea of what's going on here. Okay, so that's my angular momentum. All right, now we're gonna play some tricks. We're gonna give this equation the sugar me do, and we're gonna see what happens. All right, so let's give it the sugar me do and see what pops out. All right, so we've got a lot of tools in our tool bag that we can use to like talk about velocity, okay, in terms of other points and things like that. So let's start using some of the tools in our tool bag to sort of manipulate this guy. All right, so let's assume O is fixed. Okay, so that means that we kind of have like fixed axis rotation of this particle around O. So fixed axis rotation of P about O. So that means then that I can write the velocity in terms of what would be the angular velocity of this thing crossed with the position vector. So then the velocity of this particle, Vp, is the angular velocity of that particle crossed with the position vector that locates that guy. All right, so you guys know that because you just dominated that equation on exam number 1. All right, took it to school, picked it up at 3:30. All right, so fixed axis rotation of P about O, there's our velocity. And so we're going to plug that into this portion of the equation here. Remember, LP is mass times velocity. So we can rewrite this angular velocity vector which, remember, for us was R cross L, or I'll write it as R cross MV. Here will be R cross M times V, which is omega cross R. Right. So we've got some like multiple cross products going on here, but one thing you'll know is we can remove M or pull M out. So whether we multiply M with the second cross product or the first cross product, it doesn't really matter. So we'll end up with the angular momentum is the mass times this R cross omega cross R cross product. Okay. Sort of strange looking situation we have going on here. All right. So you're probably thinking in your head, we ran out of tricks. No, not even close. We're not even close to running out of tricks yet. We still got lots of tricks. And it's a good thing we're not adults because tricks are for kids, right? So let's pull some more tricks. All right, let's introduce a quantity of 1 into this cross product, which is the magnitude of R squared over the magnitude of R squared. Okay, we know that this is equal to 1. So if I sort of multiply the right-hand side of this equation by 1, or which is this magnitude of R over magnitude of R, then I haven't violated the laws of math. Okay, I'm just introducing some new information here. All right, then my angular velocity vector, sorry, I should be using vector notation here, will become this mass times magnitude of R squared over magnitude of R squared multiplied by this cross product, R cross omega cross R. How we doing out there? Still awake? All right, still playing tricks, still playing tricks. What I'm going to do here now is I'm going to pull in from the denominator of that double magnitude of R, I'm going to pull the denominator into the cross product. So pull 1 on magnitude of R squared into cross product. So what results is our angular velocity, our angular momentum vector is equal to mass times the magnitude of R squared. Okay, so remember I'm pulling this denominator in here for both of these two vectors R bar. So we'll end up with the vector R divided by its own magnitude crossed with omega crossed with the vector R divided by its own magnitude. Yeah, you thought we were done with tricks? No, we got lots of tricks. So what is a vector divided by its own magnitude? Hopefully you remember from statics class. All right, the vector divided by its own magnitude is a unit vector in the direction of that vector. Okay, so note here that a vector divided by its own magnitude is a unit vector in that general direction. So this is a unit vector in the direction of R. All right, it's a unit vector in that particular direction. So we end up with our angular momentum vector is m times the magnitude of R squared multiplied by this position vector lambda crossed with the angular velocity crossed with the position vector locating that guy. All right. Now I know you guys are all up on your cross product identities, but I'll cut to the chase here and say that if this has a magnitude of 1, this has a magnitude of 1, right? All we're basically doing is 1 cross omega cross 1. Okay, so the magnitude of that triple cross product is just going to be the magnitude of omega. All right, all we got to worry about is the direction. Well, if we do this triple cross product, what happens is the cross product will point back in the same direction that omega currently exists. So note, by sort of cross product rules, that a unit vector crossed with this angular velocity omega crossed with the unit vector is the same thing as the unit vector omega. Okay, they're equivalent. All right, so it's a vector that's basically been multiplied by 1 twice, and with the cross products will end up just be pointing in the original direction that it was pointing. All right, there you go. So the long story short, or getting kind of long now, is that the angular velocity vector is the mass of the particle multiplied by the magnitude of the position vector r, all in the direction of this angular velocity vector omega. All right, so remember that these are sort of scalar values, and this is a vector quantity. Now let's take a minute and see if we can notice what these things are. You should have learned about the mass moment of inertia in ME2002. And the mass moment of inertia of a particle about a particular point is simply the distance from one particle to the next squared multiplied by the mass of that particle. Well, that's exactly what we have here. So this is the mass moment of inertia of P about O. So hopefully you sort of remember this or recall doing this in 2002. This quantity, m times the magnitude of r squared, is like md squared. Okay, so mass times a length squared multiplied by this angular velocity vector. All right, so long story short, this angular momentum which we started off with as r cross L, which we know is r cross mv, is equal to the mass moment of inertia of this particle about O. We usually use the capital letter I for mass moment of inertia, multiplied by the angular velocity of that particular particle about point O at that moment. Complicated. Played so many tricks. Tricks are for kids. All right, that was magical. How are we doing out there? Math is the best. All right, so this is the angular momentum of a singular point in space about a fixed point. All right. Now, it's pretty important in this situation that O is fixed because we used the fixed axis rotation sort of definition of our velocity in this derivation. Okay. So if point O is not fixed, this sort of relationship doesn't necessarily hold. Okay. It's a little complicated, but we're going to talk about it a little more over the next few lectures. Okay. So great. That's a single particle, but we ain't in the particle dynamics class. All right, we're in the rigid body class, and we know that a rigid body is made up of infinite amount of these particles. So the idea is we want to come up with some relationship between some torque that we might apply to our piece and how much angular momentum every single particle on our rigid body has added together, right? So ultimately, remember, we're trying to find an angular equivalent to F equals MA, which is dl dt. Okay, so we want to find an angular equivalent to force equals mass times acceleration, which is this time change of the linear momentum vector. So step number one is we want to come up with an expression for angular momentum, which we've done. So that's good. Okay, so we now have h bar, which is like L bar, right? But we have that h for a single particle. Okay, I need this for a whole body. So we need for a whole rigid body. Okay? Well, if we have a body that's comprised of infinite particles, it might behoove us to add up all of the contributions of the angular momentums of all of the particles on the body to give us the entire angular momentum of that body. The way that we do that is with an integral. All right, so if you want to sum up all the contributions of all of the points or all of the little pieces that make up a body, you integrate the contribution over the body of all of those contributions. All right, so we want to extend to what would be the full rigid body. So we need what would be HO for full body. All right, so let's sort of map this and outline this, and we'll talk about how we get there. All right, so angular momentum. Now for a rigid body. So we did it for a particle, now let's do it for a body. All right, so angular momentum for a rigid body. Let's draw ourselves a picture and we'll sort of break it down. So again, we'll make ourselves our world famous mechanics potato. All right, that potato is getting a little off. All right, there we go. So our world famous mechanics potato. All right, in the center of that potato, we have some point G. It's like our center of gravity of this potato. So we have rigid body with center of gravity at point capital G. All right, now let's assume that we're going to look at one point on this body, figure out what the angular momentum of that one point is, and then sum up the contributions of all of the points on that body. All right, so let's consider an arbitrary point P. It has a differential mass because we're going to do an integration. Yeah, my S's are bad. Differential mass. Let's call it dm. All right, a differential mass. That sort of makes sense. We'll say it has velocity, which is v or vp if you like. And it's at position r. All right, so let's see what we can do to draw this. All right, so here's point P, some arbitrary point. All right, and it's located at position R. Let me get some cool colors going. So here's the position that locates P from G. And let's say that this is here, P, point P. Okay, and this guy will have a differential mass dm and a velocity v. Okay, so it will have a vector here, which is dl, the differential linear momentum, which is dm times the velocity v. All right, dmv. Ah! All right, don't want to go there. Let's also apply some angular velocity and angular acceleration to this object. All right. Let body have angular velocity and acceleration, which is omega and alpha. Looks like I have a question in the chat. Or I have something that somebody said in the chat. 11 out of 10 positive development. That was at 2:05. So sorry I'm a little late on your comment there, Katie. Okay, well, let's keep going. All right. Let the body have angular velocity and acceleration, omega and alpha. So let's go ahead and draw that in here. So let's say we're rotating in a positive fashion with angular velocity omega, and let's say that our acceleration is also positive and is alpha. All right. So we are drawing these as vectors, which are rotations, but we know with this right-hand rule that our thumb's going to be out of the page. So the rotations for this guy are out of the page, but generally they can be in any arbitrary direction. We're not confining this to 2D. We're having a general 3D derivation here. Okay. So what then is the angular momentum of this rigid body? Oh, angular momentum of rigid body. And here we have to specify about which points we have an angular momentum. Okay, the angular momentum of this body about point G is different than the angular momentum of this body about point O. And that's because if we move away from the center, different points contribute differently to the angular momentum because the position vector locating those points from where we are changes. So let's specifically talk about it at point G. The angular momentum of the rigid body at center of gravity is we're going to add up the contributions of all of the points P that exist on this body and give ourselves a definition here. All right, so that is going to be the angular momentum fully of this rigid body is the integral on this body of all of the contributions of these individual points, which is the integral of what is this dH vector, and that's integrating over the volume of this piece. So this is an integral on the volume of dH, right? Well, we can rewrite this to be not in terms of the volume, but in terms of the mass. Okay, so here, this integral, we know that the angular momentum vector dH can be written in terms of omega r squared and the mass. Okay, so here this will be m times magnitude of r squared. Sorry, not my bad. dm times the magnitude of r squared, where this magnitude of r is the distance between any of the points on the body, and this is angular velocity vector omega. Here now we're integrating on the mass. All right, so just changing our definition of this sort of aerial integral, integrating on the mass. All right, now what do we know about the angular velocity of all points on this body? Well, we showed in previous lectures that if you know the angular velocity of any point on the body, you know the angular velocity of every point on the body. And that generally means that the angular velocity of all points is the same. So omega for all points, the same. Meaning it doesn't matter which differential mass we're looking at. It doesn't matter how big or how small, where it's located makes no difference. That means that we can pull this omega out of the integral. So we're not if we integrate over the mass, over the volume, doesn't matter what point we look at it, where we are, the angular velocity doesn't depend on that mass. Okay, so we can say then that the angular velocity hg, let's pull omega out, and let's rearrange this integral, integrating over the mass of the magnitude of our position vector squared dm. All right, so we talked about the mass moment of inertia of a singular particle about a point, but you can also recognize that this integral of r squared dm is the integral of d squared dm, which is the definition of your mass moment of inertia of a rigid body. And specifically, this is about its center. Center of gravity. I'll be specific about that. Okay, so go back to your 2002 notes and look at your definition for the derivative of the mass moment of inertia of a body. That equation should be there. Hopefully it is there. The integral of r squared dm. That's one that hopefully is burned into your memory. All right. So this is the mass moment of a rigid body about its center of gravity, usually given by the variable I bar, or in this class, I'll use IG, just so we're specific about which point we're looking at our mass moment of inertia. All right. So in conclusion, the angular momentum for a rigid body is this angular velocity vector omega multiplied by the mass moment of inertia of this object about its center. Bam! This is angular momentum of a rigid body about its center. Of gravity. All right. Good. Great. Marvelous. Fantastic. So we've got a definition now for angular momentum of our rigid body. Just a reminder, I'll flip you over to PowerPoint here for a quick second. So just a reminder that your equation sheet has typical mass moments of inertia of common objects. So this is straight from your equation sheet for this class. Okay, so if you have a thin rod that looks something like this, the mass moment of inertia of this particular rod about x is 0 if it's thin, about y and z has here some value 1/12 ml squared. Okay, so just remind you what mass moment of inertia is for some common objects. For a sphere around any of these major axes, it's 2/5 mr squared. Here are some other objects, so on and so forth. Here are some other objects, rectangular prisms, cylinders, half cylinders. All of this information, reminder, can be found on the common equation sheet for this class, okay? If you're ever taking a test and you need this information, I will make it available to you, okay? All right, back to the writing pad for last thoughts, and then we'll get you out of here today. Get you out of here like you're, not, gonna go home or something. You're already home. Hopefully. All right. So next time, remember our force and acceleration analogy was something like dl dt. So next time, we do the equivalent here, which is dh dt. All right. So we're gonna have to take the time derivative of that equation up there, which seems innocuous, but actually complicated. All right. So we're getting there with our next relationship between an equivalent force equals ma. We're getting there with the equivalent something equals something angular acceleration. Oh boy, that's kind of a sad way to close the book today, but that'll be it for today. So thank you for coming. I'll stick around. People have questions in the chat. Again, good job on exam 1. I emailed all of you. If you have questions about it, please contact me and hopefully we can work through it. Okay. Have a good day. Ta-ta.